All right, so this is lesson 6, characteristics of graphs, part 2. All right, so first of all, let's talk about intercepts. Okay, so intercepts, you've seen this in algebra before, algebra 1. Surely you talked about at least y-intercepts. Here we have y-intercepts. There we go. There's my y-intercept. And we have x-intercepts. Right, all of those are x-intercepts. Now, what are they, right? These are points on the graph where the graph is actually touching one of the axes, okay? And so if we're looking at, so here's the actual function. You don't need to know that, but that's the function that we're looking at right here, at least the graph of that we're looking at. If I wanted to answer the question, where does this thing touch the x-axis? Well, it touches at 3 separate points, and I'm just going to estimate those values. Let's do the x-intercepts in red here. And I see 4 of them, right? So this one, which is, let's see, 1, 2, 3. So let's say negative 2.8, comma 0. This looks like negative 0.8, comma 0, right? It's not quite to negative 1. It's a little bit before it. Here's 1, so about positive 0.8. And then positive 2.8. So there are 4 intercepts. These are 4 points of the graph. The y-axis, where does the graph touch the y-axis? Will that be at the y-intercept? Not say intercepts, intercept, because there's only one, right? Right there at 0, comma 1. Okay, and so notice something, right? For all of the x-intercepts, they're always a number, comma 0, a number, comma 0, right? They all have a number followed by 0. So in general, whenever we're dealing with an x-intercept, you should always have an x value, comma 0. For y-intercepts, it's the opposite. It should be 0, comma some y value of the graph. Okay, and that makes sense, right? If you're looking at the y-intercept, look at it horizontally, it's not to the left or to the right. It's right in the middle, so it should have an x value of 0. Same is true for the x-intercepts. They all have a height of 0, and so you would say that the y value for all those points would be 0. All right, so there we go. That's the x-intercepts and the y-intercepts. Okay, so let's talk about this one here. Here's another graph. Let's find the intercepts, and while we're at it, look at it, determine where is it increasing, where is it decreasing, where is it constant. Okay, review that as well. So first of all, the intercepts. I'll try to stick with x-intercepts being in red. This graph touches the x-axis twice, right? Right there and right there. And so that would be what? 0, 0. And right here, which would be 1, 2, 3, 3, comma 0. Okay, y-intercept, you may notice something special about that y-intercept. It's this point right here. Turns out it's actually the x-intercept as well. So if the graph happens to pass through the origin, it shares an x-intercept and a y-intercept. Okay, those intercepts are the same point. Okay, and those are the intercepts, right? We don't have any other ones. But let's talk about the intervals that it's increasing and decreasing. So I'll just jot this off to the side here. Where is this thing increasing? Remember to trace it from left to right. So starting down here, from left to right, it's increasing until it hits this point. Then it starts decreasing, right? So that first little track upward started right about negative 1.5 or negative 3 over 2, if you want to write it as a fraction, and stopped increasing here when x was 0. So this increases from negative 3 over 2, or negative 1.5, comma 0. Okay, so let's see if it does it anywhere else. Decreasing. At this point, it starts increasing again. So here we go again, from here to there. So when x is 2 until x is 3, we are increasing. Okay, from here to here, decreasing. But at that point, it starts going up again. So that would be from 4 to 5. From 4 to 5, we are increasing. Okay, remember, these are not points. These are intervals, right? Interval notation. So x values, where does it start? Where does it stop? Okay, decreasing. Okay, increasing. At this point, it's now decreasing. And from here to here, it's decreasing. There are 2 points where it is decreasing. They're in green right now. So that would be from 0 until x is 2. From 3 to 4. Okay, again, these are intervals. Now, here's something that happens, okay, that people do sometimes. So careful to avoid this. Let's say this is the interval you're looking at here. People are tempted to put the y values instead because you're kind of looking at the y values to determine if it's increasing or decreasing. So they'll say y is 0, well, -2 to 0. And that is not an interval as far as increasing or decreasing. The y values tell you how much, like how high or how low something went, does not tell you where. And if you're asking for the intervals on which something is increasing or decreasing, you are looking for where. You can think about it like mile markers on the interstate, right? If you're driving, you're going up a hill. If you're trying to tell somebody about this really steep hill, you wouldn't tell them, well, it's at negative, or it's at 5 feet below sea level, and then it goes up to 0 feet. Okay, that gives them a description, but does not tell them where, right? You would tell them start at mile marker, well, -2 in this sense, and continue to mile marker 0, right? That way they can actually go behind you and figure out where this happened at. Okay, so that's how you can think about that. Okay, so that was intercepts. Let's talk about roots, sometimes called zeros. I want to say that Alex refers to these as zeros. So it really depends on who you're talking to or what book you're using, what software you're using. Roots, zeros, they mean the same thing. Okay, a root or a zero is very similar to x-intercepts, but they're not the same thing. Okay, an x-intercept is a point on the graph. A root or a zero of a function is the input needed to get an output of 0. So what is the number that you plug in to get y to equal 0? That's what we're asking for. And so in other words, if you're looking at a graph, there's a very good chance, well, if you find any x-intercepts, those are definitely going to be some zeros. So here we're looking at 1, and here we're looking at 2. Now notice I'm not listing these out as points, right? I'm not thinking about them as points. I'm thinking about them as if I plug 1 into the function, right, into this function up here, I get 0. If I plug 2 into the function, I get 0. So 1 and 2 are my zeros, or my roots. Okay, so that's what it says at the bottom here. For what values of x is the function equal to 0, 1, and 2. Okay, but like I said, x-intercepts and roots are zeros. They are not necessarily going to be exactly the same. It's possible to have zeros that are not x-intercepts. And so here's a good example. Just looking at the graph right here, we don't have any intercepts, right? What are the intercepts? None. Well, at least no x-intercepts. I guess I asked intercepts in general. No x-intercepts. We do have a y-intercept though, right? It crosses the y-axis here at 0, 1. So let's say that 0, 1 is the y-intercept. But we do not have an x-intercept. But the question about roots or zeros is what would you have to plug into this function to get it to equal 0? So to figure that out, I'm going to solve x squared plus 1 equals 0. And we'll just do that real quick. If I subtract 1 from both sides, I cancel out that plus 1 on the left. 0 minus 1 is negative 1. And then I use the square root property, right? You can think about that as doing the square root of both sides. And that'll give me positive and negative, the square root of negative 1. Okay, and depending on how much algebra you've taken, you might say that that doesn't exist, or you might say that it's an imaginary number, right? It's definitely an imaginary number. The complex number world is interesting enough. Okay, so those are roots, right? Those are zeros. If you plug them into the function, and the point of this lesson is not to go into detail about I, but I squared equals negative 1. And so negative 1 plus 1 is 0, right? So it's possible to have roots, right, or zeros, but not have x-intercepts. Okay, let's talk about extreme values here, also known as maximum and minimum values. Okay, and so there's a distinction to be made between local and absolute minimum and maximum values. Okay, so let's talk about local first. Well, let's talk about absolute first. I lied. Let's talk about absolute. Absolute's easy. You look for the highest point on the graph. You look for the lowest point on the graph. Those would be the absolute min and max values. So here's my lowest point. Okay, it is equal to negative 5. Let's say we'll call this the absolute. Make sure I have space here. Let's write it out. This is the absolute minimum value. It's negative 5. In other words, it's 5 down, right? That's how low it is. And then it's usually the next part of the question is, where is that located? And it's located when x is, let's just say negative 1.5 or negative 3/2. I'll say at. Or negative 1.5. That'd be the absolute minimum. The absolute maximum, I see a couple of options here. But this one on the right side can't be it because you see how it's an open circle, right? That means there's no point there. So the one on the left is the absolute maximum. It is equal to 4, right? It's up 4 when x is equal to 3. So the absolute maximum of this graph is 4 when x is equal to 3. So those are the absolute minimum and maximum values, extreme values. Okay, so then let's talk about local. So local is a little bit different. The thing with local is that the point, if it's going to be a local maximum or a local minimum, it has to be surrounded by some other points. We'd say it has to be in its own little neighborhood. Okay, so for example, this point right here is not a local minimum, because if you look at it, we don't have anything to the left of it. It's not in its own little neighborhood. Okay, I would consider a point in a neighborhood if there's some points to the left of it and there's some, the points are graphed to the right of it. Okay, so there's points to the left and points to the right. That would be a neighborhood existing around a point. And so for it to be a local anything, it has to be in a little neighborhood. And so this one is out of the picture. What about this one right here? Okay, in that little area, right? If I ignored everything outside of that box, within that little box, that's my graph now. That is the highest point. Okay, so in that box, it is the local maximum. Hopefully that makes sense, right? If you throw away the rest of the graph and focus just on this little rectangle, that little rectangle has a graph in it. The highest point in that box is 0, 0. So I have a local maximum. The value, the height is 0 whenever x is equal to 0, right? It's the point 0, 0. Okay. I look at this point as a potential local minimum, but I'm missing a point there, so I can't say it's that one. This is an interesting one right here. Okay, this one's interesting. I guess it kind of depends on how you look at it, but does it meet the definition of a local maximum, right? Well, this one right here certainly does not. Okay, because if you look at it, it's in a neighborhood. It has points to the left of it and points to the right of it. But unfortunately, it does not have, it has points to the left of it and points to the right of it, but it's kind of disconnected. And this point in particular, the point to the right of it is up high, right? It's up high. And I'm realizing there's a problem with this graph, by the way, because this is supposed to be the graph of a function, and it's definitely not the graph of a function, right? Because we have two y values. Y is 0, y is 4, for a single x value 3. Okay, so that's throwing me off a little bit. So I guess we'll just decide which one of those is supposed to be an open circle here. Judging by my notes, this one was supposed to be an open circle. And so, well, that rules this one out as a local maximum. And this one's not a local maximum because if you go to the right of it, you're up here. Okay. All right, so we'll just say that's that. Let's go to the next point. The next point is this one right here. So in that area, if I drew a box around it, that point is the lowest point, right? Again, if I ignored all this outside of it, just looking at this, that's the lowest point. And so I would say that I have a local minimum at 1 of 1 whenever x is equal to 4. Okay, I think that's all of them. So that one. Yep, okay. That one's a little trickier than it needed to be. Okay, so local max, local min. Absolute max, absolute min. Okay, this is what I wanted to get to in the last few minutes. All right, so I want to solve some equations, and we're not talking about solving these by hand. This is something I think we're going to do tomorrow, solving some of these by hand. Not all of these. But what I want to do is talk about how you can use technology to approximate the answers, okay? And so this is where you'd want to use a graphing calculator if you can. What I'm going to use is desmos.com. And pull that up as soon as I can find it. Okay, so 5x minus 4 equals x squared plus 2. All right, before I pull it up, I'm going to graph the left side. I'm going to graph the right side as if they're their own equations, okay? And I want to know where they're equal to each other. Well, that's going to be where they intersect each other, right? And so if I can just find the point that these two intersect, then that solves the equation for me. All right, I'll be specifically looking for the x value. All right, so let's look at it. All right, I think I already have this pulled up. And so here's y equals 5x minus 4. Here's y equals x squared. Now, maybe it's easy to see, maybe not, but these two intersect here at 1.382. It's an approximation, right? And again at 3.618. Now, I'm not so worried about the y values. Remember, I'm looking for x. So there's my two probable solutions, or approximated solutions. X equals There we go. Shrink that. X equals 1.382 and 3.618. So, this is not going to be the way to do it if you're in the middle of your calculus, taking an exam and you want to find the exact solution for some particular problem, right? That's not the way to do it. But if you're trying to solve a real problem, right, and you just need some sort of an estimate for the solution, right? Like 1.38, maybe this is dealing with finances, $1.38, right? That's a good estimate. $3.62 would be a good estimate. Okay, so that would be this one. And the cool thing about this is, yeah, that gives me an approximated solution. If I solved it by hand, I can always just compare what I found with this, and we'll see how close we are. If I go to this next example here, this is an uglier one. And so I definitely don't want to do this one by hand. Sine of x, I'll graph, right? We kind of know what that looks like if you took trig. And log base 4 of 5x. Okay, so let me hide those and let's try that out. What does this graph look like? So there's sine. There's log base 4 of 5x. They intersect when x is 0.302. So that's my approximated solution. Okay, I did want to mention another way to do this, right? So you see this third option down here. So you could graph them as two separate things, or think about what happens when you subtract two things that are equal to each other. All right, do that with something you know. All right, something that's equal to something. 2 and 10 over 5. If I were to subtract those two things, I would get 0, right? Because they're equal to each other. So what I'm actually looking for, if I want to, I can think about this as one equation where I subtract one side from the other side. Then I just have to look at the graph and find where does y equal 0. Okay, so that's another way you can do it. Let's see. So, all right. So here's the graph. If I subtracted them, where does it equal 0? At 0.302. The y value is 0. All right. So if you put them all together, you can kind of see it looks bunched up right here. I can zoom in though. So where does the red line and the blue line intersect? Same place where the green line is located. It's 0. All right, and that'll be time. So I'll stop recording.